Have you ever built a simple circuit, flipped the switch, and watched your LED flash brightly for a microsecond before burning out? It's one of the most frustrating moments in electronics. But why does this happen? Today, we're going to break down the interaction between an LED, a capacitor, and a resistor to find out how to prevent that fatal error. Let's imagine a DC circuit connected directly to an LED and a capacitor. On the surface, this seems perfectly logical. The battery provides the voltage, the potential energy, and the components draw the current to do work. But in the world of electricity, logic is often betrayed by physics. When the switch is closed, the capacitor acts as a reservoir, trying to charge up almost instantly. It demands a massive surge of current. Because there is no resistor to slow this flow, Ohm's law is bypassed. The current isn't limited by resistance, so it shoots through the LED at maximum speed. The LED has no time to dissipate this heat. The internal junction overheats, the semiconductor breaks, and poof, the LED is destroyed in milliseconds. The solution isn't magic, it's simple resistance. By adding a current-limiting resistor in series, we introduce a known value of opposition. According to Ohm's law, voltage equals current times resistance. The resistor drops a specific amount of voltage across itself, forcing the remaining voltage to limit the current flowing through the LED. It acts like a speed bump for electrons, ensuring the flow is safe and consistent. Now, let's look at the capacitor. It's great for smoothing out power, but it can also be the cause of trouble. Without the resistor to limit the inrush current, the capacitor acts as a short circuit the moment power is applied. When you connect the battery, the capacitor is empty and acts like a wire. Current rushes through the resistor and LED. The LED is at its brightest. As the capacitor fills up with electrons, it creates back pressure, voltage, that fights against the battery. Because the pressure is equalizing, the current slows down. You will see the LED gradually dimming. Once the capacitor is full, matches the battery voltage, the current stops completely. The LED is off. Have you ever wired an LED directly to a battery, then added a capacitor in parallel thinking it might protect it? It seems logical. The capacitor stores energy, the LED uses it, and everything shares the same voltage. But here's the catch. In a parallel circuit, both the LED and the capacitor see the exact same voltage from the source. The capacitor doesn't sit in the way of the current. It sits beside the LED. When power is applied, the capacitor quickly charges, pulling a surge of current, but not through the LED. Meanwhile, the LED is still directly exposed to the full voltage of the battery. If that voltage is too high, the LED draws excessive current and can burn out. So what does the capacitor actually do? It smooths the voltage. It absorbs spikes and stabilizes the supply, making the LED appear more steady. But it does not limit current. And that means one thing. Without a resistor, your LED is still at risk. Understanding these interactions isn't just theory. It's the difference between a fragile prototype and a reliable circuit. Next time you wire up your electronics, remember, the resistor is your best friend. Thanks for watching, and don't forget to like and subscribe for more deep dives into the science of engineering.